This is the PreLab lecture for Experiment 7, where we will be determining the Ka and Kb of a couple of systems. Now on Blackboard you will find the template for the Excel to use for this experiment. And if you open it up, there are 2 pages to this Excel sheet. So on the first page it lists the blank student data form. And you'll notice it's divided into 3 sections. So the first experiment, part of the experiment, we will be determining the equilibrium constant of acetic acid. And then in the second part, we'll be determining the equilibrium constant of an unknown weak acid. And for the third part, we will be determining the equilibrium constant of a weak base. Now notice there are 2 pages to this workbook. There's the blank student data form, so where you will type in your pH values. So let's say for the pH of the weaker acetic acid, I determine that pH to be 3.55. Now these numbers I'm just making up for the illustration purposes, but if you click on the full calculations page down at the bottom, you'll see that it automatically imports those numbers into the second page. So notice for the grams of sodium acetate, it says 0 right now. If I go to this other page and I type in the grams of sodium acetate, so I'm making up a number, and this number that I've put in automatically gets transferred to the other page in the spreadsheet. So in that page here where there are blanks, you will be calculating these values using the pH and your balanced chemical equation. So in the first system, you'll be determining the Ka using 3 different values. First of all, we'll be using a 0.5 molar acetic acid solution. So I'm just going to use HA for my generic equilibrium reaction for my acetic acid, rather than drawing out everything for acetic acid. Well, if I only have 0.5 molar acetic acid and nothing else in there, I can set up my ice table, and it's very similar to some of the problems that we did in chapters 15. And because we don't have the Ka, that's what we're looking for. Normally we're having to solve for X. This time we can measure X from the pH. And remember, pH equals the negative log of the hydronium ion concentration. So you measure the pH. Let's say we measure the pH to be 3. To get my hydronium concentration, so remember the H plus concentration is going to be 10 raised to the negative pH, so it's 10 raised to the negative 3.00. Now in part B of part 1, we've still got acetic acid. This time we're only using a more dilute concentration of acetic acid, so 0.2 molar. But in part C, we're using 0.5 molar acetic acid, but this time we're adding sodium acetate. So notice that we're adding the conjugate base to the system. So we'll have to take that into account when we set up our initial concentrations, when we set up our ice tables. So going back to our reaction, so we know that we're starting off with 0.5 molar HA in part C. We're going to assume the hydronium concentration is 0. But the A- concentration, we have to calculate it based on the mass of the sodium acetate and put in the molarity. So we have to calculate this based on the mass that we measured out. And then we can set up our change, and then we can do our products over our reactants to get our Ka. So remember, the A- concentration isn't 0 initially. We've added some by adding the sodium acetate. So we have to take the mass, use the molecular weight to get the number of moles, and then use the volume of the solution to get the molarity, and that's what goes in for our initial concentration of our A-. Now in part B, we have an unknown weak acid. and we're trying to find the Ka of that unknown weak acid. And we're going to tell you that's a monoprotic acid. And so we're going to measure the pH of that solution, and we have a 0.1 molar solution of that weak acid. So the calculation is very similar to what we did in part 1A and part 1B. But in part B, we're adding 5 mils of 1 molar sodium hydroxide to 25 mils of the unknown acid. So when we're adding the sodium hydroxide, we're neutralizing part of the unknown acid. So I've got a weak acid plus my sodium hydroxide. And this is a neutralization reaction when you add the acid and the base. And neutralization reactions are one-way reactions, so I don't have to worry about an equilibrium with the neutralization. So that will make my salt and water. So Na plus and the A minus. So in this reaction, we have to determine what the limiting reagents are. So let's say I do this calculation and I find out that I've got 4 millimoles of HA and 1 millimole of sodium hydroxide. Well, when I look at this, since there's a 1-to-1 mole ratio of the HA and the sodium hydroxide, I know that my sodium hydroxide, since I have less of it, is going to be my limiting reagent. So I'm going to lose 1 millimole of sodium hydroxide as it reacts with the HA, and so it's going to consume 1 millimole of my HA. So I will have 3 millimoles of HA left over, none of my sodium hydroxide, but this will produce 1 millimole of the A minus. Now notice that I have an excess of the weak acid, and I've added some A minus, so this is going to be a buffer situation. So now that I've taken care of the first reaction, that neutralization reaction, I can then look at the equilibrium reaction of HA going to H plus and A minus. Remember, that's an equilibrium reaction, so that's a two-way reaction. So I have to put in my initial concentration of A minus based on my moles of A minus and my total volume. So be careful, you make sure you take into account the total volume when you calculate the molarity of the A minus. And then the molarity of the HA comes from the remainder of the HA that's left over from the neutralization reaction divided by the total volume to give me my concentration of HA. Then I can set up my reaction still where I do my change, so minus X, and then plus X. And then once I've got all of those values in, I can just set up my mass action equation. So it's products over reactants, and I can determine my Ka value. So part C, you will work very similarly to part B. And then in part 3, rather than working with acids, we'll be working with bases. So in part 3, we will be looking at the equilibrium constant of a weak base. So remember, if we write our generic equation for our base, so we add the base in water, the base will become protonated by the water. So we'll have our HB plus and our OH minus. And we are given the initial concentration of our base as 0.50 molar. And that's the only thing we have in our solution is just the weak base. So we consider the other concentrations to be initially 0. And we set up our change, our minus X plus the X, and then plus the X. So our Kb will be equal to X squared over the 0.5 minus X. Now we will be measuring the pH of the solution, but we need the hydroxide concentration. So we'll be measuring the pH, but we need the hydroxide concentration. So if we have the pH, but we need the pOH, we can take 14 minus the pH to give us that POH. And then to get the hydronium concentration, it's 10 raised to the negative POH to get the hydronium concentration. So that'll be our X value. And this will allow us to determine our Kb. Now in part 3b, we will be adding 5 mils of 0.1 molar HCl to 20 mils of 0.5 molar unknown base. So again, we have a neutralization reaction whenever we're adding an acid and a base, and that neutralization reaction is a one-way reaction. So we're adding HCl to our base. This is a one-way. So we'll protonate our base to make the HB plus, and we'll make Cl minus. So I have to determine my limiting reagent. So I need to find the amount of HCl that I've added. And I've added 0.1 molar, and I've added 5 mils. And if I multiply these together, this gives me 0.5 millimole. And for my base, I'm adding 20 mils of 0.5 molar. And if I've done my math correctly in my head, that'll be 10 millimoles of the base. Well, this is my initial concentration, but my change, I notice that my HCl, that's my limiting reagent, I lose that 0.5 millimoles of the HCl, and I lose 0.5 millimoles of the base to get a total of 9.5 millimoles. But when I neutralize the acid in the base, that will make 0.5 millimoles of the HB. So I have my number of millimoles of my protonated base as 0.5 millimoles, where milli just means 1,000th. So once I take care of that one-way reaction, the neutralization reaction, then I can deal with the equilibrium. Our equilibrium is the base in water, and it becomes protonated by the water to give us our hydroxide concentration. Well, using the moles that we had before, I think this was 9.5 millimoles. But if it was 9.5 millimoles, if I divide it by my total volume, which is 25 mils, I will get the molarity of the base. And my conjugate acid, I think that was 0.5 millimoles. But if that was 0.5 millimoles of the initial concentration of HB, we would also divide it by the total volume. And this would give us our molarity of the HB. So these tell us our initial amounts in our ice table. Now we can set up our change. So minus X plus X of the HB plus X of the hydroxide. And again, this hydroxide concentration we can get from the pH. So we measure the pH using our electrodes. We convert it to the POH, and then we take the POH to get the hydroxide concentration, using the fact that 10 raised to the negative POH equals the hydroxide concentration. So remember, that's our X value that we can plug into our mass action equation to find the Kb of our equilibrium constant. And when you turn in your lab report, make sure you turn in both pages, the student form that has your numbers, and then the full calculations that show all of your calculations and your values. So do not discard a value even if it deviates significantly from the others, and do not do any approximations. The math is easy, and you will not get the same answer as your lab instructor if you do an approximation. Be sure to do all of these calculations in Excel so that there are no rounding errors. These boxes that are highlighted yellow will automatically transfer your values to the next page so that you can do your calculations in Excel. Thus, the yellow cells on the next workbook page are locked for editing so that there are no discrepancies in values. This is the end of the PreLab lecture video for Experiment 7. Good luck calculating your data.